Hello everyone, I am Vinod Jayasundara from A-Star Singapore. In this study, we investigate the use of capsule networks for optical flow estimation and then the use of estimated optical flows for action recognition. Why do we need a capsule encoder for optical flow estimation? The estimation task becomes complex since the inputs are raw pixel intensities. Raw pixels often contain sparse motion information cluttered with non-motion information. Also, pixels at various spatial locations with similar intensities may have different relative motion. Therefore, optical flow estimation is more convenient if motion information are unentangled and better coded. However, existing networks such as the FlowNet have shallow CNN encoders which are not often adequate for this. Hence, we have the need for an advanced encoder. We hypothesized that a capsule encoder could be an excellent candidate for this task. Due to the inherent properties of capsule networks, it can provide finer-grained, concise, motion-specific, and more interpretable representation for better correspondence matching, better generalization for out-of-domain classes, with comparatively lesser ground truth data and a lot less computational complexity. FlowCaps is the first study on capsule networks for optical flow estimation to the best of our knowledge. FlowCaps achieves better optical flow estimation and subsequent action recognition performance for several benchmark datasets with nearly 94% reduction in computational complexity. We also investigate on the capabilities of FlowCaps. Our proposed capsule encoder consists of a convolutional layer followed by 3 convolutional capsule layers which are dynamically routed to each other. The capsule encoder output is kept to one channel following the capsule representational assumption. The reduced representation is then fed to the contracting part followed by the expanding part, which are heavily simplified versions of FlowNet. The simplified contracting part comprises of 7 convolutional blocks and the expanding part 4 blocks of upsampling with deconvolutional layers. The typical loss function for optical flow estimation EPE only considers the magnitude in its calculations, whereas the angle which carries important information is omitted. Also, the L2 norm is highly susceptible to outliers with higher values. Therefore, we propose the following weighted sum with log-cost loss for the magnitude loss since it is more robust to outliers and a variation of the cosine similarity for the angular loss which adaptively scales the loss with respect to the magnitude of the ground truth optical flows. We propose 2 different approaches based on the number of consecutive frames considered for prediction at a time, based on the intuition that the extra frames can provide additional contextual information and that it is more natural to perform action recognition on a segment of frames rather than a pair of frames. Let's have a look at the performance of the proposed FlowCaps model. For most benchmark optical flow estimation datasets, we can observe a clear improvement with FlowCaps compared to other state-of-the-art optical flow estimation approaches. Segment-wise model outperformed frame-wise model across all the datasets, indicating advantage of our capsule encoder and better exploitation of contextual motion information. Here, we present our performance for several benchmark action recognition datasets. We can observe that optical flows estimated by FlowCaps can be better adapted to other tasks such as action classification than those by the FlowNet. Here, we present a few visual results obtained from FlowCaps and compare with those obtained from FlowNet. We can clearly observe a visual improvement in comparison to the ground truth optical flows. We present a similar comparison for the KTH dataset as well as the UCF dataset. To evaluate the out-of-domain generalization capability of FlowCaps, we train on 5 classes of UCF and test on 88 other classes. This figure shows the differences in the testing APE values obtained from the 2 models for these out-of-domain classes. Except for one class, FlowCaps demonstrates better generalizability over FlowCaps over all the action classes. To evaluate the FlowCaps' ability to perform well with lesser training data, we train the models with a fraction of the available training set while retaining the full testing set. As the training dataset size decreases, the performance gap between the models clearly increases, suggesting that FlowCaps increasingly performs better than FlowNet as the amount of available training data decreases. For more information, please join the Q&A session for the paper ID 975. Thank you for listening.